Dear children, today I would like to discuss the coordination number. Myself, Dr. Digna Origis. Structure of the complex. We know the structure of the complex depends upon mainly two factors. First one is the coordination number. Second one is the stereochemistry. Coordination number is the atoms or group of atoms attached directly to the metal center. Stereochemistry means how the coordinated atoms are arranged in space. So these two factors determines the structure or geometry of the complex. Coordination number, the definition. The total number of points of attachment of ligand to the central metal ion is termed the coordination number or ligancy. In a complex, more precisely say an inner sphere complex, the ligands are attached directly to the central metal atom or ion. These ligands form the primary coordination sphere of the complex, and their number is called coordination number of the central metal atom. You can see here a cobalt hexamine complex, hexamine cobalt 3 chloride complex. In this complex, the number of ligands attached to the central metal atom, that is cobalt. Here you can see 6 ammonia ligands attached to the cobalt. So its coordination number is 6. But this chloride is present outer sphere, or it is a counter-ion part, not a ligand directly attached to the central metal atom. So here considering 6 is the coordination number. Okay, and these ligands are responsible for the geometry of the molecule. So it's an octahedral complex. So it is the primary coordination sphere of the complex. That inside the primary coordination sphere of the complex, the number of ligands which represents the coordination number. As in solids, a wide range of coordination numbers can occur, and the origin of the structural richness and the chemical diversity of the complexes is the ability of the coordination number to range up to 12. Okay. Depending on the coordination number, the structure and geometry of the coordination compounds found to be different. The coordination number of a metal atom or ion is not always same as the composition of the solid. Example, some solvent molecules may simply fill spaces within the structure and not have any direct bonds to the metal ion. Such additional solvent molecules are called solvent of crystallization. Here you can see a complex of cobalt in which the water molecules, there are 4 water molecules attached to the cobalt atom, and there are 2 chloride ions attached to the cobalt atom, and the complex is found to be octahedral. Okay, its coordination number is 6 because in this complex 4 water molecules and 2 chloride ions are direct contact with the metal ion, that is cobalt atom here. Okay, so its coordination number is 6. But there are 2 water molecules present here. These water molecules, no direct interaction or attachment to the central metal ion. So such solvent molecules are called solvent of crystallization. The coordination number of a metal atom or ion is not always the same as the composition of the solid. Here the composition of the solid or a complex is that COH2O4 Cl2 to H2O. That is its actual composition. But coordination number is 6, and these 2 water molecules act as solvent molecules. They simply fill the spaces within the structure and not have any direct contact with the cobalt atom. So it is these two water molecules are called solvent of crystallization, but these water molecules, that is here and here, these water molecules are ligands, that is have direct contact with the central cobalt atom. Okay. X-ray diffraction shows that the cobalt chloride 6H2O, here COCl2 6H2O, it's a composition of the solid. Okay, but the complex composition is that COCl2 OH2 4 times and two uncoordinated water molecules occupying well-defined positions in the crystal. So, single crystal X-ray diffraction shows the composition of the solid that is different from the coordination number of the metal ion. Okay. So such solvent molecules that have not have any direct bonds to the central metal ion, that is known as solvent of crystallization. Factors affecting coordination number. The size of the central metal atom or ion. Second one is the steric interactions between the ligands. Third one is the electronic interactions between the central atom or ion and the ligands. So these three factors, that is size of the metal atom or ion, steric interactions between the ligands, electronic interactions between the central atom or ion and the ligands. Conditions for higher or lower coordination numbers. The size of the central atom or ion, which depends on the whether the metal atom acquires the higher or lower coordination numbers. The larger radii of atoms and ions favor higher coordination numbers. Higher coordination numbers are also most common on the left of a period. We know left side of the periodic table contain the ions with larger radii. So they favor higher coordination numbers. You can see from the example MoCN8 4 times. Here molybdenum atom has the coordination number 8. So these types of higher coordination numbers especially common when the metal ion has only a few electrons. Because a small number of valence electrons means that the metal ion can accept more electrons from the Lewis base. Here the Lewis base is cyanide ion. So 8 Lewis base can donate electrons to the central molybdenum atom. So you can see from this table the ionic radii of the lithium ion is 59, sodium ion is 99, and for potassium ion 138 and rubidium 148. You can see its coordination number. For lithium 4, sodium 4, but for higher coordination numbers 6 is for potassium and rubidium ions. So as the radius increases, the coordination number also increases. Atomic radii of metals generally increases with the coordination number of the lattice. You can see the coordination number 12, the relative radius is 1, for 8.97, 6.96, 4.88. Okay. The size of the ions that is ionic radii, increases with coordination number. You can see from this plot the coordination number versus ionic radius. Here you can see the variation of ionic radius with coordination number. For coordination number for lithium, only up to 8. Its radius is near to 50. But for sodium ion, it is about 99. Its coordination number increases than lithium. Okay. For potassium, you can see it is up to also similar to sodium, but it shows more coordination numbers than sodium. So its radius range is about near to 150. So the size of the ions increases with coordination number. Here you can see the metal ion. High charge on the metal ion has small ionic size. So it prefers low coordination number. In the case of this metal ion, here low charge on the metal ion. So its ionic size is big. So it favors higher coordination number. Once again, I will tell you, if the charge is high, size is low, so it favors low coordination number. If the charge on the metal ion is low, its size is high or big, its coordination number is high. Second condition, whether the metal ion favors low coordination number or high coordination number, is that the steric interactions between the ligands. Bulky ligands result in low coordination numbers. You know, if the ligand is bulkier, that means high steric interaction. So it prefers low coordination number because when these ligands attach to the metal ion, there is more steric interaction. So more attractive power occurs between the ligands and the metal ion. Due to steric interactions, there is repulsion occurs between the ligands. So it prefers low coordination numbers. If the ligands are also charged, where the ions have larger radii, result in low coordination number. The ligands are charged, so its ionic radii larger, so it results in low coordination numbers. They are especially common when the metal ion has only a few electrons because a small number of valence electrons means that the metal ion accepts more electrons from the Lewis bases. Such atoms are less able to accept electrons from any Lewis bases that are potential ligands. Every geometry has a specific coordination number. Every complex with a specific coordination number will have a choice of several possible geometries. For example, we know the coordination number is 4. It has different coordination geometries. The metal ion can prefer tetrahedral or square planar geometry. The coordination number of ions in lattices is related to the ratio of the radii of the ions. Here you can see so many coordination number 4, 6, 6, 7, 8, 8, 9, 12, etc. Its radius ratio is different. Okay. For coordination number 4, its radius ratio is 0.2 to 5. It is preferable to tetrahedral geometry or coordination polyhedron is tetrahedron. If it is 6, its radius ratio is 0.414. It is octahedron. For coordination number 6, its radius ratio is 0.528. It is trigonal prism. And coordination number 7, it's about 0.592 radius ratio. It is capped octahedron. There are 8 coordination numbers with different radius ratio, that is 0.6454 for square antiprism, 0.668 for dodecahedron, 0.732 for cube. So different radius ratio having different geometry of the coordination compound. For coordination number 9, it is tri-capped trigonal prism with the coordination. Radius ratio is 0.732. For coordination number 12, for icosahedron, its radius ratio is 0.902. Cubooctahedron, it is about 1. Okay. So higher coordination number, the relative radius ratio is high. That we have already seen. Coordination number and hybridization. For coordination number 2, its hybridization is SP. Its arrangement is linear. For coordination number 3, SP2 is the hybridization. Trigonal planar is the arrangement. For coordination number 4, we know for the same coordination number, different geometries or arrangement of ligands to the central metal ion is possible. That is, you can see tetrahedral and square planar. Tetrahedral geometry, the hybridization is sp3. For square planar geometry, hybridization is dsp2. For coordination number 5, trigonal, bipyramidal and square pyramidal are the geometries. Its hybridization is sp3d. And for octahedron geometry, the coordination number is 6 and its hybridization is sp3d2. So coordination number and hybridization is related. Okay. Determination of coordination numbers. How we can determine the coordination numbers of a central metal ion. The coordination number of an atom can be determined straightforwardly by counting nearest neighbors. A common way to determine the coordination number of an atom is by X-ray crystallography. If we take a single crystal X-ray diffraction for the complex, we can easily determine its structure and its coordination number if there is any solvent of crystallization. What are the bonding between the molecules or with the central metal atom. So this can easily determined by X-ray crystallography method. When a single crystals of a compound can be grown, X-ray diffraction gives precise shapes, bond distances and angles of the complex. Other methods you can use for the determination of coordination numbers. One is neutron diffraction. Second one is electron diffraction. Third one is nuclear magnetic resonance. Fourth one is vibrational spectroscopy. And the next one is electronic spectroscopy. These methods can be used for the determination of coordination numbers, but more precise method is by X-ray crystallography. Thank you for your attention.